Hello and welcome to Crush Particle Analysis Problems with Hound, presented by American Pharmaceutical Review and sponsored by Unchained Labs. My name is Mike Auerbach. I'm the Editor-in-Chief of American Pharmaceutical Review, and I'll be the moderator during today's event. In today's webinar, you will learn approaches to address particle characterization needs across different material types and in different industries, how Raman and laser-induced breakdown spectroscopy can complement traditional particle analysis counting and morphology measurements, and advantages of an all-in-one automated system for particle characterization and identification. In addition, this event will hold a live question and answer session at the end of the presentation. To ask a question, click on the Ask a Question tab on the right side of your screen. Please take note, the right side of your screen also features an overview of this webinar and more information regarding our speaker. If you have a technical question during the event, click the Test Your Connection button at the bottom of your screen. From there, you can access additional webinar support. Finally, we encourage you to use the social media widgets beneath the webinar to share with your friends and colleagues. And now, allow me to introduce today's presenter. Robin Sweeney is the product manager for Hound and Bouncer product lines at Unchained Labs. Robin earned a Bachelor of Science degree in Biology and Biomathematics from the University of Scranton and a PhD in Biomedical Engineering from the University of Arizona. Her graduate research focused on optical biosensor development. At Unchained Labs, Robin focuses on applications and advancements of QC platforms for biologic drug development. Robin, welcome to the webinar.
Thanks, Mike, for that introduction. Today, I want to walk you through a couple of different case studies to show you how you can crush particle analysis problems with Hound. I don't know how many of you were like me and joined the crowds in picking up baking as a hobby over the last year, but I'm sure someone here has felt the pain of adding the sugar to your recipe. Or wait, was that the salt? I've had to make that taste test more than a few times, and luckily in this situation, that's easy and safe to do. If I had put the salt in instead of the sugar, the dish would be ruined. So it's critical to know which one I actually added, and I can't tell them apart by eye. Particles are very similar to this, especially in biologic drugs. Many particles are small white dots floating around, and it's nearly impossible to just look at the particle and figure out what it is. It could be an aggregated protein, an excipient precipitated out of solution, or a contaminant, and none of those things really look that different. Particles that occur throughout various industries can be catastrophic to your process, so knowing what a particle is made of and where it came from are crucial to the success of your product. Particles may be there intentionally, like an API or an excipient, or unintentionally, like a protein aggregate, a material that's been degraded, or a contaminant in the product. Whatever the particles are, you need a way to characterize them. Most technologies that characterize particles require the user to have an idea of what the particle is. For example, FTIR can be used for polymers, but not metals or other elemental particles. SEM-EDS can identify those metals, but not most organic materials. The list shown is just a small subset of the possible particle types you may run into, meaning that you need a lot of flexibility to handle all these kinds of particles. This leaves you needing a variety of instruments, a good hunch about what your particle is, and the ability to transfer your particles between instruments just in case that hunch is wrong. That's where Hound comes in. Hound combines microscopy with up to 3 types of spectroscopy: 785 nanometer Raman, 532 nanometer Raman, and laser-induced breakdown spectroscopy, or LIBS. These technologies allow Hound to characterize the count, size, and shape of your particles, while further getting you the chemical identification and elemental identification for you to get a complete characterization of any particle that you come across. Hound can handle a wide variety of sample types due to the highly flexible nature of the instrument. In our case studies, you're going to see a couple of different sample preparations. For particles in a liquid suspension, you can filter out the particles to isolate them on the surface of a gold-coated filter round. Alternatively, if you have a dry powder, you could simply spread that across the surface of that filter round. Sometimes, though, you have particles in suspension and you want to keep it that way. Whether it's because your particles are amorphous or another reason, the liquid suspension can simply be pipetted onto a gold-coated wet round and analyzed directly. Once you start up particle analysis with Hound, the automated microscope scans a sample area to image and count all of the particles. The size of the particles is also calculated along with numerous morphological parameters. At this point, the exact location of your particles is known, so automated spectroscopy can take over to identify your particles. For organic and inorganic compounds, dual Raman lasers are there to get you a chemical fingerprint that can be used to determine what a particle is made of and therefore where it came from. The 785 nanometer laser is great for organic and inorganic compounds, while the 532 nanometer Raman laser is great for organic and especially proteinaceous materials. When a Raman spectrum is collected, it's compared against a built-in reference database that contains over 150 common contaminants to find a matching material for that particle. Sometimes, though, you want to know the exact source of the particle, or you have a unique material in your process. In those cases, you want to expand and customize the database so that it can be fully tailored to your process. For metallic and elemental particles, laser-induced breakdown spectroscopy, or LIBS, is able to get you that elemental fingerprint of the material. Just like the Raman database, Hound does come with a built-in, but still fully customizable LIBS database. While the default database in this case contains more than 50 common materials, you can fully customize this to tailor it to your process as well. Let's talk a little bit about why you might want to customize that database. Doing this allows you to get a highly specific match for a particle. For example, our database has aluminum in it, which is shown on the left. But a specific brand of crimp cap that you use in your process could have a unique peak like the one seen here on the right. While both spectra are aluminum, the custom reference spectrum allows you to get a much more specific match to narrow down the exact source of your particle. In our upcoming case studies, we're going to talk about quantifying the match to get the strongest match possible. So I want to tell you a little bit about how Hound does that. Match rank is the parameter that Hound uses to quantify the strength of a match between your unknown particle and the reference material in either our default or your custom databases. Match rank is calculated by multiplying the Pearson correlation coefficient by 1,000. So you end up with a value between 0 and 1,000, with values closer to 1,000 indicating a stronger correlation. A lot of factors go into influencing the strength of this correlation, but the overlap between the peak position of your unknown sample and your reference sample is the biggest influencer on the strength of a match. Let's dive into our first case study now. The user had structural debris that needed to be identified to provide insight into the cause of material failure. Structural debris can come from a huge variety of places. For example, it could be residue left behind from a water pipe that failed at your house. Characterizing this debris can point you to the material that failed and therefore show you the weak points in the structure that could be corrected. For this case study, the user had 3 different structural debris samples and needed to identify the individual components in each debris sample. They also had the 3 raw materials that each structure was made of. These raw materials were used to create a custom reference database and that custom reference database was then used to quantify the ratios of each material in each debris sample. The first raw material actually ended up having two varieties. The outer layer of this was similar to borosilicate, while the inner layer was similar to low alloy steel. And both of these varieties were added to the custom database as materials 1A and 1B. Material 2 was similar to dolomite, while material 3 was similar to aluminum oxide. All of the raw materials were added to a custom database, and the 3 structural debris samples were then compared against that database for a specific breakdown of how much each material is present in the structural debris sample. The first mixed structural debris sample had many particles that varied in size. Hound identified just under 1,700 particles in about 90 minutes total. Of those exactly 1,691 particles, a majority were material 1, with about a third being material 1A and about 2/3 being material 1B. A small fraction of the particles, under 1%, were material 2, while not many more were material 3. Mixture 2 had fewer particles, but these particles were a lot larger. For mixture 2, 135 particles were identified, and a large majority of these were material 3. Just about a fifth of the particles were found to be material 1B, and materials 1A and 2 were not present at all in this mixture. Moving on to material 3, this had a few large particles and many small particles, so we're looking at a variety of particle sizes. One interesting thing about mixture 3 that you can see from this image is the particles are actually adhered to duct tape, because that's how the researchers collected the particles from the structure failure. The duct tape substrate presented no problems for Hound because LIBS was used, and duct tape is actually LIBS inactive. Of the 418 particles that were identified from this sample, about half were material 1B, just under half were material 2, and a small fraction, under 5%, were material 3. All of these mixtures were analyzed automatically by Hound, and this was all actually quite fast. Mixture 1 had the most particles at about 1,700, and between imaging the sample, counting the particles, and identifying those 1,700 particles, Hound completed this in just about 90 minutes. Hound was able to provide highly specific information on the material-specific distribution of particles in each of these 3 structural debris case studies. This information helps to provide insight into the failure based on knowing what raw material was present in the form of debris. This was made possible by the ability of Hound to create a custom reference database. Without this ability, we might not have known, for example, that material 1 actually contained those 2 varieties layered together. Let's change topics slightly to discuss our second case study. This case study focuses on particles in biologic drugs. Sometimes in these biologic drugs, compounds such as polysorbate 20 are used to stabilize the monoclonal antibodies. When this PS20 degrades, oleic acid can be released into the product, and that oleic acid can induce aggregation. Our second case study brings in this concept in the sense that the free oleic acid in the buffer is thought to be impacting the protein. The user here suspected oleic acid was inducing aggregation of their protein and wanted to find out if that really was the case. So with this in mind, the user wanted to determine if oleic acid was present in their protein aggregates, and if so, they wanted to estimate the relative percent of oleic acid present in each aggregate. This information could then be used to determine if more oleic acid leads to more protein aggregation. To start, references were collected from the raw materials that the researchers had. So we created a custom reference from oleic acid and one from the protein. Looking at these two spectra, it's clear that you can easily distinguish pure protein from pure oleic acid. Now the question remains, can we identify mixed particles that contain some percentage of protein and oleic acid in various quantities? While we had the pure reference materials, that oleic acid and protein, we didn't have access to any mixed references for oleic acid and protein aggregated in known ratios. Instead, we filled the reference database with composite protein oleic acid spectra that were calculated across a full range of ratios. The actual oleic acid content per particle that we are going to find was unknown going into this, so we created that full range of composites calculated from 100% oleic acid to 100% protein at 1% intervals. This reference database was then used to analyze aggregated samples that had a range of buffer oleic acid content. Let's take a look at this reference database that we created. What you can see here are those pure oleic acid and pure protein spectra that were actually collected from real samples. These spectra were then combined in various ratios to calculate the composites that you see here. And this was to fill in the gap in that reference database. So between pure oleic acid and pure protein, we're seeing composites for 75% oleic acid, 50% oleic acid, and 25% oleic acid. But remember, this is just a subset of the database. This was actually done at 1% intervals. What you can see with this is these composites start looking pretty similar. Since we're looking at these 1% intervals in the ratio between oleic acid and protein, we expect that the spectra are going to look quite similar to each other within a narrow range. Because of this, we need to quantify the best match. So the highest match rank was used to quantify the relative percent of oleic acid versus protein per particle. In the example shown, the particle spectrum had the highest match rank against the 13% oleic acid and 87% protein composite, which indicated to us that this was going to be the highest match. So this particle was considered 13% oleic acid and 87% protein. Samples with low, moderate, and high oleic acid content in the buffer were analyzed in this way to determine if increased buffer oleic acid content caused increased particle oleic acid content. For each sample, 50 particles greater than 5 microns in size were analyzed. When the buffer had low oleic acid content, so did the particles. Only 10% of particles contained oleic acid, and of those 10%, they only contained up to 3% oleic acid. When the buffer had moderate oleic acid content, the oleic acid content in the particles increased. So in that case, just under half, 46% of the particles contained oleic acid. And those particles contained up to 9% oleic acid per particle. Following this trend, when the buffer had high oleic acid content, so did the particles, up to 14% oleic acid per particle. Further, a significant majority of these particles did contain oleic acid. 86% of the particles in this sample were found to contain any oleic acid at all. While it was initially suspected that oleic acid was inducing protein aggregation, Hound confirmed that there is in fact a concentration-dependent aggregation due to oleic acid in the buffer. Using the calculated composite spectra that we talked about, Hound was able to discern differences between protein aggregates with various concentrations of buffer oleic acid and even estimate the relative percentage of oleic acid content in these complex mixed particles. As you can see through these case studies, Hound really does have particle analysis covered, no matter what your needs may be. Whether you have a fine, powder-like debris sample, particles adhered to a surface, or complex amorphous protein aggregates in suspension, Hound can handle these samples and get you the count, size, shape, and identification for these particles. These case studies span just a fraction of the applications that you could imagine Hound being a key technology for. Hound can handle a wide variety of sample types, making it flexible for characterizing the count, size, shape, and chemical or elemental identification of a wide range of particle types. And this can be done either manually if you have just a few particles, or automatically if you have hundreds or thousands of particles like we saw in our case studies today. With that, I'm happy to take any questions you guys have about characterizing particles with Hound.
Thanks, Robin, for your excellent presentation. I'd like to remind everyone that you can submit any questions you have for Robin in the Q&A box on your screen, and we'll get to as many as we can. So let's now take a look at the questions that have been submitted. And our first question for Robin is, it looks like a few different sample prep methods were used in these case studies. Can you describe sample prep with Hound?
Yeah, a couple different sample prep methods were used in these case studies. The first one that was used was using what we call adhesive rounds, and this is specific for LIBS. You're adhering particles to a nitrocellulose filter and putting that right onto Hound. The second case study actually analyzed particles in suspension using a wet round. So in this case, the particles were simply pipetted onto the wet round and analyzed directly on Hound with the sample still in suspension. We have a couple other ways that you can do this. The most popular actually is a filter round. So this is the gold-coated filter that you would filter your sample through to isolate particles on top. But if you have a sample that doesn't really fit any of those sample prep methods, you actually don't even really need to do too much prep at all. You can simply take whatever your sample is, whether it's a piece of a whole raw material or it's a large particle, and you can actually just plop it right on the stage and analyze it directly without any preparation.
Mm-hmm. Excellent. Thank you so much for your answer, Robin. Let's take a look at our next question. Why are the consumables gold-coated?
The filter round and wet round that I talked about are both gold-coated, and there's a couple reasons for this. First, when you're doing dark field imaging with that 20x objective that's on Hound, it increases the contrast so that you're getting a high contrast between your particles and the background. On the spectroscopy sides of things, though, gold is Raman inactive, so the gold coating helps to reduce background noise. That way you're not getting any signal from the consumable itself, and you're getting the cleanest, lowest noise spectrum possible.
Okay, thank you very much for that answer. Let's move on to our next question. Can you use Raman and LIBS on the same sample?
Yes, you can. If you're going to do this, we would recommend that you use Raman first and then do LIBS. And that's because LIBS does ablate a small amount of the particle, so you don't want to do that until after you've collected your Raman. In fact, you can use all three different lasers that are on Hound on the same particle. So if you have a true unknown, typically what you'll do is that red 785 nanometer Raman laser, that's a good catch-all, you'll do first. Then you'll move on to the higher powered 532 nanometer Raman laser, and finally LIBS in that order to get the most information possible from one particle.
Mm-hmm. Excellent, thank you. Let's take a look at our next question. Can you characterize just a subset of particles in cases where you have a lot of particles?
Yes, you can. And there's a couple different ways that you can characterize a different subset. So if you have a lot of particles and you just want to analyze a percentage of them, you can do that. You can say analyze X number of total particles, either random particles, to get a random population or the largest particles in the sample. If you want to get more specific than that, though, you can actually do size-directed identification. For example, sometimes you care about particles within a certain size range if your API is only bioactive at a certain size. So in that case, you would do size-directed ID to say identify all particles that are 5 to 10 microns in size, or identify all particles that are over 100 microns. And then the final way you can do this is with morphology-directed ID. So if you have a case where maybe you're looking for fibers, you can say identify only particles with a fibrosity longer than this cutoff, or something like that, whether it's a fibrosity or a rectangularity, any of the morphological parameters can be used as cutoffs.
Okay, excellent. I'd like to remind all of our viewers that if you have any questions for Robin, please type them in the Ask a Question box right now, and we'll get to as many as we can. Let's look at our next question. Can Hound be used in a 21 CFR Part 11 compliant environment?
Yes, it can. Hound has a bunch of 21 CFR Part 11 tools that help you remain compliant in this environment. So these include things like an audit trail or signature requirements on all of your data. And then whether you're in that 21 CFR Part 11 compliant environment or not, Hound actually has automated reporting tools. So every experiment that you do, you can generate an automated report that's going to provide you with a PDF that lists out everything that was done in that experiment, from the methods used, the exposure times for the lasers and the lights, all of that, all the way through all of the data that's collected.
Okay, thanks, Robin. Well, it appears that we have gone through all of our questions. So at this point, I would like to thank Robin for sharing her knowledge with us today, and also offer a special thank you to Unchained Labs for sponsoring today's event. Please keep a lookout for an email containing a link to view this webinar on demand and to share with your colleagues. Thank you for joining us today, and please enjoy the rest of your day.